Assalamu alaikum everyone. Today the date is 18th 18/04/21. Today we'll continue from the previous lecture where we stopped. This is the second part. So what we have done, uh, what we have done so where we stopped last class. Let's check. So this was our last class where we stopped. Okay, we stopped here, right? We find the expected value. We find the expected value of this, right? Of our signal, expected value. And we have seen the average value of this transmitted signal is 0, right? Now we will continue this lecture to 18/04/21. Okay, so we have seen the expected value or the average value of this transmitted signal is 0. Now we'll try to find what is the spectrum of this transmitted signal. So we would like to find the spectrum of the transmitted signal or transmitted bit, whatever. No, not transmitted bit, it's a transmitted signal because we are talking about xt, which is actually combination of the all the bits k value goes from minus infinity to plus infinity. So definitely it's a signal. Now what is our let's check what was our signal. Xt was k equal to minus infinity to plus infinity. Ak is our bit, random bit, and pt is the pulse t minus t. Here this is the pulse, right? This is our pulse. So it's a shifted pulse actually by kt. And here this amount ak is the kth signal. Because of this randomness of this signal, this xt, this becomes random, right? Okay. Now this kt, okay, next slide. Okay, for this kth bit, it can be either 0 or 1, right? We have seen it previously. Now this either it could be 0 or 1. This is a random in nature, right? It's a random in nature. Means ak can be either a, like m in amplitude in a physical representation, or minus a, right? These two, they are also random. We also know the our PT have a 1 or 0 pulse width from minus t by 2 to plus t by 2, right? We have seen it in our previous uh, slides. We also have seen that this AK is IDD. Sorry, IID is independent identical distribution, right? We have seen all this stuff in our previous example. Now, we like to uh, let me close. We like to see. We like to see what? We like to see the spectrum, right? We like to see this, the spectrum of the signal, transmitted signal. How we can have the spectrum of this transmitted signal? We can have it by Fourier transform. So our signal was xt, right? If we do the Fourier transform of xt, if we convert it to its Fourier, then we can have xf. So this is a time domain signal. This is a frequency domain signal. So we can see the spectrum in frequency domain, of course. So how can we have it? If we do Fourier transform. So our Fourier transform will depend on our time domain signal integrated over minus infinity to plus infinity. We already have seen it, right? It is minus j 2 pi ft dt. This is the Fourier. What is the expected or average value of this Fourier? What is the expected value? The expected value of this Fourier or this frequency domain signal is expected value of this one, where we have minus infinity to plus infinity xt e to the power minus j 2 pi ft dt, right? Now we can insert this expected value at the expression inside, right? We can rewrite it as follows. We can rewrite it minus infinity to plus infinity expected value of x t e to the power minus j 2 pi ft dt. Now we already know that this expression, the expected value of the or the average value of the transmitted signal is 0. This tends to 0. If this happens, then actually the expected value or average value of the Fourier, that becomes 0. This is very surprising. Expected value of or average value of previous case, this one, this one, this is understandable. That the average value of transmitted signal is 0. Now the spectrum, expected value of the spectrum is also 0. How come? Very surprising result. If the spectrum of the transmitted signal is 0, or the Fourier transform of the transmitted signal is 0, what does it mean? Mean that we do not need to transmit a signal at all, because this is 0. It cannot be. Means something is wrong. Somewhere something is wrong. Why we get this result? There is a reason. This is because the Fourier transform. What we did? We did the Fourier transform of a signal. Which signal? This signal. We did the Fourier transform of this signal. What is this signal? The nature of this signal xt. This is a random signal xt, right? We have seen that xt is here. This xt have this expression ak. Because of the randomness of this bit, this whole signal becomes random signal, and we cannot apply a Fourier transform of a random signal. That's why we get these surprising results. Fourier transform can be applied for deterministic signal or continuous signal, but it cannot apply to a random signal. But how do we will find the spectrum of this random signal, right? The what this gives that the average value or expected value, average value of spectrum is 0, which doesn't mean that, so it doesn't mean the spectrum is 0. The average value of a spectrum is 0 doesn't mean the spectrum itself 0. So spectrum itself is not 0. Okay. Now question is how to measure the spectral content. Now a big question. How to measure the spectral content. A random signal. This is a big question. We have just seen that average value of the spectrum is 0, though it doesn't mean the spectrum itself is 0. Means spectral content is not 0. So if spectral content is not 0, how to measure it? How to measure the spectral content of a random signal? The answer is power spectral density. The answer is power spectral density. So what is the power spectral density? Power spectral density will actually give us the spectral distribution. Spectral distribution of power of a, because it's random signal, so it's a random signal. So what the power spectral density gives us? The power spectral gives us the spectral distribution of power of this random signal. So we will get the distribution of power of this signal. So how do we do that? To do that, we have to do the autocorrelation. So to compute the power spectral density, to calculate the power spectral density, we have to do the autocorrelation. So if we do the autocorrelation of our signal, we will actually end up the power spectral density. Now, for autocorrelation of which signal? We know the expression of autocorrelation is R. We are do auto. There are two kind of correlation. One is cross correlation, another is autocorrelation. Cross correlation means if you do correlation, right, like uh, with another signal, with X your signal with another signal, then this is the, if you do your correlation with yourself, X X, that's the expression with tau. So how do we write it? Autocorrelation of any signal is expected value of X t and X t plus tau. If we can find this value, we can find the autocorrelation of this signal. So if we do the autocorrelation, we will end up with the power spectral density. And so this one, power spectral density, and if we do the autocorrelation of a signal, you will find the power spectral density of that signal. This is only true. This is only, this is conditional. Only true for a specific kind of signal. Only true for what kind of signal? If signal is a WSS. WSS. What is that? Wide sense stationary. Is that term new to you? Wide sense stationary? Wide sense stationary? No. You already studied this kind of signal, wide sense stationary process. So WSS, wide sense stationary process, you already studied in your which course? RSP course, random signal and processing course. Probably chapter 7 or 8. The last chapter you studied in your random signal processing should be the wide sense stationary. So when we call some process is a wide sense stationary, for example, xt, a signal xt. When I call this signal xt is a wide sense stationary process. So xt will call a wide sense stationary if if eh, if it satisfies to agenda. If its mean, its mean value and its autocorrelation both are time invariant. In very, if they do not depends on time, it's in the mean value do not depends on time, and autocorrelation do not depends on time, then we call it a wide sense stationary process. Okay. Okay. Now what we will do, we will try to do this one. We try to find the autocorrelation of signal X. Okay. So how we do that one autocorrelation? If we do the this operation, we find the expected value, then we can find this autocorrelation. So expected value of X t and X t plus tau is what? So expected value, we know X is this signal, k equal to minus infinity to plus infinity is our AK pt t minus kt multiplied by another signal. Let's say m equal to minus infinity to plus infinity am pt e minus mt. Here this one is our this value, this is our xt, this one is our xt plus tau. So rewriting it's just rewriting it, so I missed this part, here it will be t plus tau. I missed this tau. Right, so we rewrite it in this way. Now we will do the, we take this our expected operation inside, we'll insert it here, so expected value of ak am, just insert it. Okay, now very fantastic stuff will come, this expected value of, so let's write it separately here, so expected value of what happens ak and am, remember we defined it previously that ak and am, probably where, let's check it, we defined it, it's a iid, it's a iid, where we defined it, uh, no, not that far, somewhere here we define what kind of process it is. Yeah, okay, yeah, we defined it previously that ak is iid, it's an independent identical distribution, which actually was expressed by this one, right? Because they're independent, but they are identical distribution. Because they are independent, the expected value of ak and am, you can write it separately. We know it from RSP, right? If some processes are independent, the expected value, uh, we can separate it. Same thing, we can do it here. We can do it here. So we can write expected value is E ak am, and because individually they are, it's 0, this is also 0, expected value, because they are random in nature, so the this expression comes out to be 0 because this is a IID, independent identical distribution. Now These terms is true for k not equal to m. This is the condition. K not equal to m. The expected value of ak and am will be 0 only if ak not equal to m. Right? But what happens if they are equal? Next page. What happens if k equal to m? What will happen? K equal to m, right? So we can rewrite that equation, right? Uh, our previous equation. See, we'll rewrite this equation. Here, these are k and m are the same. What will happen? If k and m are the same, we can rewrite it. We can rewrite k equal to minus infinity to plus infinity. So expected value, they are equal. So ak square. So pt t minus kt and p t t plus tau minus kt. Right? How we have this? If they are square, they are the same. What will happen? The probability that ak equal to a is what? Half. The probability of ak, sorry, ak equal to minus half, that's actually minus a equal to half. What is this expected value then? You can find the expected value of ak square will be, we have calculated it previously, and they are not equal, right? Into a square plus half into minus a square. What will happen? A square. That's the equivalent value for expected value of ak square. So we will put it here. Now this will be replaced by a square. So this is replaced by a square, right? Now what is a square? Amplitude square. Amplitude square is nothing but the power. We can call it data symbol power. Data symbol power or symbol power P, PD, whatever. Okay, so we can replace it. So we can rewrite it as PD. We can replace and write it again. K equal to minus infinity plus infinity pt t minus kt pt t plus tau minus kt. Now this equation, this part, is a t dependent, time dependent, right? So depends on t. So if it depends on t, then this is actually the this one. So let's see this one. We got it from the expected value of this one, this one. This is our result. So the expected value E x t x t plus tau. This is the equivalent. We are actually deriving this equation. So because this solution depends on t, this expression, our expected value, is not a wide sense stationary process, because wide sense stationary process, their expected value and autocorrelation do not depends on t. Here the autocorrelation depends on t. So it is not a wide sense stationary process. So if it's a wide sense, if it's not a wide sense stationary process, we can do many kind of analysis, and we cannot eventually find the power spectral density. We cannot find the power spectral density. We cannot find the power spectral density of this signal, because we know the power spectral density will depend on the autocorrelation of this signal. If we have the autocorrelation of this signal, this one, then we can have the power spectral density. But this is not a wide sense stationary process, so we cannot have a power spectral density. Means we cannot have the distribution of power of the spectrum, which we intended before, right? So what to do? We do some tricks. Okay. To have it, so our xt, rewrite the equation k equal to minus infinity to plus infinity. This is a random data. It's the pulse pt t minus kt. This is our delay, right? This is a fixed delay, t delay. What we will do, we'll add a random delay to it. For example, t0. We just add. So here t0 is a random delay, random delay, right? So t0 is a random delay whose distribution is 0 to t. So it's a uniformly distributed actually, right? So t0 is uniformly distributed. So uniformly distributed random delay. From 0 to t. So the how it looks like, the power spectral density of this uniform delay looks like this: 0 to t, and distribution rate is 1 by t. So how it looks like, so we give it a name. So f t0, f t0, this one, this t0. So how it looks like, the f t0, it have this distribution. If I write it in the equation, then it's 0 to t. So 0 to t. right? So T0 distribution is 0 to T. At that distribution, its temperature is 1 by T. Otherwise, it's 0. Okay, that's its distribution. Now, we will rewrite this equation again. The expected value of x t x t plus tau. Remember what was our uh, previous equation? PD the power k minus infinity to plus infinity. This one, Mm, this one, this one. We are rewriting this one. So we try to find the expected value, right? Oh, we could have right here. Anyway, so we write it. So in pt t minus kt minus t0 pt t plus tau minus kt minus t0. Okay, we just rewrite this equation. This one. This one. See, we inserted a random uniformly distributed random delay. So t kt t0, which is actually the pt and pt plus tau. This one. Yeah. Okay. Now the what it gives me the expected value or the average with respect to t0, because our uh, expected operator is inside, so we get a average or expected value with respect to tau t0, with respect to t0, because a we inserted an operator, random delay. We inserted a random delay t0, right? Now so we will rewrite it. If we rewrite it, then pd equal to minus infinity plus infinity. What we try to find the average of the expected value with respect to, or the expected value of the summation with respect to t0. So what we will do, we'll actually integrate it to minus infinity to plus infinity. The pulse, we have to add the this ft. So f t0 pt t minus at minus t0 pt t plus tau minus kt minus t0 d t0. What we are doing actually, we are averaging with respect to t, which is a random relay. So what we did actually, to get the average, we actually multiply the expression by the distribution of the random delay. Right? We are trying to get the average. Okay. What is this average value? Is nature is this from 0 to t. So we can rewrite this PD. So f t0 is this value 1 by t. This value is 1 by t. So 1 by t equal to minus infinity to plus infinity, and this limit will be this one 0 to t, from 0 to t. So pt t minus kt minus t0 pt t plus tau minus kt minus t0 dt0. We will do some substitution. So here let t0 plus kt equal to t0 tilde if t plus kt. So t plus kt is t0 tilde. If this is the case, then d t0. So dt0 with respect to t0. So this will be 1. This will be 0. So it will be t d t0 tilde, right? If this is the case. Now rewriting the okay, PD t equal to minus infinity to infinity. So here 0 t0. So 0 to t was our limit with respect to t0. So if t0 is 0, then t0 tilde will be kt. So this will be our kt. Trying to say is our previous limit was 0 t0. So t0 is 0, t0 is 0. So t0 tilde will be kt. So our limit will be kt for 0. For t means t0 is t. So it will be k plus 1 t. That's our limit changes. So pt t. So t0 kt becomes t0 tilde. So minus t0 tilde. So pt t plus tau, and this one is t0 tilde, t0 tilde, and dt0 is dt0 tilde. So still now here something happens. You see this one here, each integral start from So each integral start from kt to kt to k plus 1 t, right? And from here we can see k itself is minus infinity to plus infinity, to minus infinity to plus infinity, means we can actually combine this. So by combining we can write it, we can write it pd by t minus infinity to plus infinity, as usual, pt t minus t0 tilde p t plus tau minus t0 tilde d t0 tilde. Okay, so we still didn't get what we expected, so we will do again substitution. What we will do, t plus tau minus tau 0 tilde, this expression we say it's actually t0 prime. If this is the case, t0 prime, then what is t0 prime means? So this will be differentiation, dt will be 0, tau will be 0, this will be minus d t0 tilde equal to t0 tau prime, right? Again we substitute it, we'll replace it. So if we replace it, pt t, now you see it was minus infinity, tau 0 tilde was minus infinity. So if this is minus infinity, so what will happen? Minus minus becomes plus infinity. So it is a plus infinity to minus infinity. So our limit changes. So pt t minus tau. So t minus prime equal to t0. From here we can find t0 prime minus tau, minus tau, minus tau. And pt equal to t0 prime minus d t0 prime. This this notation, the sign, if we bring it here, we can actually, means by changing, we can change it to minus to plus, because of the, by changing the sign which was here before. Okay, because it's a negative sign. Okay, so what we find here, very interesting expression we find it here. We find pt now depends on tau. Actually I write it, let's write it nicely. Let's write it nicely. And pd t minus infinity to plus infinity pt t0 prime pt t0 prime minus tau d t0 tau. Here we can see this expression do not depends on t. So this expression does not depend on t. T. It's only, so depends on what? This one, tau. Tau. It depends on tau. Now, this expression E x t x t plus tau here, this is actually our xt, guys. This xt, this one, this one, this is our xt. Now we can say this xt is do not depend on t and it's only depend on tau, means it now becomes the time invariant system. So we can say it's a WSS, wide sense stationary. If it's wide sense stationary, then we can find the expected value of this one is equivalent to, which is the autocorrelation of this function, is r of x tau. Now this expression satisfies. So this expression we can rewrite. I can rewrite it here. Yeah, I can rewrite here. So we can write this PTT, this one, we can write it as a R PT PT tau, following this system. We are making an autocorrelation. So this is the autocorrelation of the pulse PT. This is the autocorrelation function of the pulse PT. So we can have this statement that the expression of this one is independent of t, which makes it wide sense stationary because it's become only depend on tau, becomes time invariant, and autocorrelation of the PTT of this function pulse is the have this expression. Okay, so we can write so our expression are xx, which was our first expression, which is expected value of x t x t plus tau, is actually PD by T and this expression R of PTT PTPT tau. So we can see the autocorrelation of the signal X is here. Autocorrelation of the signal is depends on the autocorrelation of the pulse. If we do the Fourier transform, then this is Fourier transform, then we can have S of S XX power spectral density. If you do the Fourier transform of the autocorrelation, we got the power spectral density Vd by T. Same thing. This will be the, we do the Fourier transform. We got the power spectral density, which is S Pt Pt. Very interesting expression. So the power spectral density of signal is we have a relation with the power spectral density of the pulse, or the Fourier transform of the autocorrelation, which actually gives the power spectral density, will give the power spectral density of the pulse. Now, because this pulse PT is a deterministic signal, this pulse is a, it's not a random process. If it's a deterministic signal, we know that the how this power spectral density of this deterministic signal is actually called the energy spectral density. So we called it as a energy spectral because of this nature. PT is a deterministic signal. Okay. So what we just find that the power spectral density of our signal, power spectral density of our transmitted signal is actually have a relation with the energy spectral density of the pulse by this relation. Okay, so uh, so we can find a relation of the power spectral density and the energy spectral density of a transmitted digital signal. We will stop here. We will stop here our recording and continue from the next lecture. Assalamu alaikum.